Hi, welcome back to the YouTube channel. If you don't already know, my name is Abdul Wahab Anuoku and I'm a college math instructor. In today's video, we're going to look at how to find out if a function of several variables is differentiable, and if it is, where is this differentiable? As well as we'll look at how to find the partial derivatives of such functions. Okay, before we get right into the video, if you're new to this channel, please like and subscribe, like the videos and subscribe to this channel, and also endeavor to share these videos in your social media so that other students like you can benefit from this knowledge and videos. So let's get started into solving this problem. All right, so we have this function, and if you note, as we have mentioned in previous videos, we can look at f of xy as say we have a function, a square root of another function, g of xy, where g of xy is this polynomial, right? Now, in the previous video, we already mentioned that what all polynomial functions. So when you have polynomials, basically, so all polynomials are continuous. They're continuous and differentiable everywhere. So that means I can find the derivatives of them. I can find partial derivatives of polynomial functions, and I can conclude that they're continuous at any particular point when we graph the function. Okay, now once we know this, now when you look at f of x, the only restriction that you have is the square root, right? I mean, if the question was this, f of xy equal to 17 minus 2x squared minus 7y squared, we would have concluded that f is differentiable everywhere. This would have been our conclusion, right? Everywhere. Which what I mean by everywhere is any xy, right? In r squared, this function will be differentiable there. Okay, but now we have a restriction, which is the square root. So that tells us that what this function f of xy that we have as square root of this g of xy, what happens is that what this function is only differentiable on the domain of f. Because in the first one, the domain of f of xy would be the real r square. So the domain of f of xy in this case would depend on the restriction on this by this square root, right? So first of all, we need to find the domain of f, and then we conclude that what on that domain the function will be differentiable because the function that we have is a polynomial. I hope that line of thought makes sense. Okay. So now, what do we need to find the domain of this? So what is the domain of this function? Because we have square root, the only time this function would exist is when inside of the square root is greater than or equal to 0. So the only time this f of xy will exist, which constitute the domain, would be when the inside of the square root, which is g of xy, is greater than or equal to 0. So this would form the domain. So any xy that satisfies this, then would be in the domain, right? So basically, all we are having from here is what 2x squared plus 7y squared must be less than or equal to 17, right? So on this domain, f of xy is differentiable everywhere. Is differentiable. Let's put it that way. Differentiable. So this is what we need. So f is differentiable only on this domain, right? Where on this domain that's where xy will satisfy that. So let me just write the domain properly. Any xy such that 2x squared plus 7y squared is less than or equal to 17. And this is actually equation of an ellipse. So this is equation of an ellipse, right? So you can draw the region where this function is differentiable. That's basically the answer to the A part of the problem, right? And the second part is to find the partial derivatives. Okay, it's to find the partial derivatives. Okay, right. So we already know that what f of xy is just square root of 17 minus 2x squared minus 7y squared. Now, we are going to use chain rule to solve this problem. So we are looking for the derivative of this with respect to x. So first of all, let's make a substitution. Let's say the inside of this function is u. Now, this implies that what is equal to square root of u. Now, we are going to use chain rule to solve this, which means fx would be given as what? Del f del u times du dx. So basically, this is what we need to figure out. Now, du dx, we can quickly find this. Du dx would be what? Derivative of 17 is 0. Derivative of minus 2x squared, that will be minus 4x. Derivative of minus 7y squared, that will be 0 because there's no x there. So we are finding derivative in terms of x. So the du dx will be minus 4x. Now, what about the del f del u? What would that be? Derivative of this function. What would that give us? Now, this is a polynomial function, not a polynomial per se, but it's um, it's a function of, it's a polynomial of fractional powers, right? So how do we find the derivative of this? Is basically how we find the derivative of polynomials, which is 1 over 2 u raised to power 1 over 2 minus 1. Okay, so that will give us 1 over 2 square root of u. Now, if you simplify this, this is what you have. Now we can bring everything back to here, which means del f del u is just 1 over 2 square root of u times the u dx, which is minus 4x. Okay. Now we can just finish the problem, which will give us minus 2x all over square root of u. And what is square root of u? Don't forget u is what? 17 minus 2x squared minus 7y squared. So basically what happens is chain rule, we differentiate the square root of the function, then we multiply it with this with the derivative of the inside of the function. So in doing the second part, we can quickly use this methodology, knowing that it is chain rule. We can quickly just find the answer to that. So the first thing again is we'll find the derivative of the outer function, which is the square root, right? Don't forget that f can be written as what? 17 minus 2x squared minus 7y squared all raised to power 1 over 2, right? So first of all, take the derivative of the outside function, which is 1 over 2, multiply it by derivative of the inside with respect to y. So derivative of the outside, again, we have 1 over 2, just bring 1 over 2 here, then the function raised to power 1 over 2 minus 1, then multiply that by derivative of the inside with respect to y. So derivative of 17 is 0, minus 2x squared will be 0 as well. Derivative of minus 7y squared will be minus 14y. Okay, so 2 into 14, that's minus 7. So we have minus 7y, so multiplied by 17 minus 2x squared minus 7y squared raised to power minus 1 over 2, which will give us, when we write this using indices, we'll get this raised to power 1 over 2. Okay, so this gives us the answer to the problem, and then if you like, you can write this as square root of right. Okay, so right, and as you can see, we talked about being differentiable, right? You can see the partial derivatives are also continuous whenever we are talking about the inside of this ellipse, right? So it will not be differentiable when at the boundaries. So let's correct that. at the boundaries, so this must not be equal to 0. So this must be greater than 0. This must be less than 17. And of course, this must be less than 17. It's within the inside of the ellipse that this function will be differentiable, right? Because when you check the partial derivatives, which talks about the derivatives of the function, you will see that what we have square root in the denominator, and you know that what the square root must not be 0. So that means the equality must not hold, right? If the equality holds, that means that what 17 will be equal to 2x squared plus it will be equal to 2x squared plus 7y squared, which will now be make the denominator equal to 0, and then that will be undefined. Okay, so the boundary of this ellipse would not satisfy the differentiability condition only when we think about the inside, only when this thing is, the inside of it is greater than 0. That is the only time we can properly have partial derivatives and then the differentiability of the function. So thank you for this, for staying to the end of this video. So this um, I mean, there are several kinds of problems like this, and I would indulge you to look at other problems of similar nature and try your hands on them. So see you guys in the next video.